Ah. All right. So let's look at what we're doing here. Today is just lecture on chapter 5 and 6. On Wednesday, we have a quiz on force and work scheduled, but I think that is best postponed to Monday, the 4th of October. So make that change in your calendars. We're going to postpone our quiz to next Monday instead of Wednesday. And I think I will change the due dates for mastering physics and for PIP to, well, let's change that to Monday night. So I'll give you an extra week on those. Okay. Does anybody have any questions on that? And remember, we're going to be on campus on the 6th of October for a experiment in Newton's second law. Okay. All right. So does anybody have any questions?
I had a question over the homework.
Okay.
For chapter 5 on mastering physics, it was 5.115.
Okay, I need to get the book. Ah. Okay, 115. Ah, okay. This one is actually quite subtle. What was the source of your question?
I guess I'm kind of stuck on what I should break down to figure the problem. Just trying to get started, I guess.
Okay. Okay. Well, let's draw it. Okay, so here's the idea. In position A over here, we have a ball of mass M. This angle is beta. And let's see. So we cut the horizontal string, the ball swings as a pendulum. Position B is the farthest to the right that the ball goes. And these two angles here are equal. What is the ratio of the tension in the supporting string B to its value at A before the string was cut? So let's do a free body diagram for the mass in position A. We have mg we have the tension in the string here at an angle beta. And we have, let's just call this T1. So now we want to solve for the tension T here. And in the vertical direction, we have T, so this is in position A, T cosine theta minus mg equals 0. Well, that doesn't even, we don't even need this other equation here. So T equals mg divided by cosine theta. Now, situation B is a little bit interesting here. For the free body diagram at position B, we have mg, and we have the tension T at this angle beta. But there's a problem here. In position A, the acceleration is 0. So I can write this. It is incorrect to write T cosine theta minus mg equals 0 for position B, because that is wrong. The acceleration is not 0 in the vertical direction. It's not moving, but that's because it's at a turning point of the motion. But the acceleration here is in that direction. So what we have to do is we have to write down an equation here for which we know the acceleration. So let's continue this here. Now, if this is the angle beta, then this is the angle beta right here. Now, what about in this direction along the string? Is there any acceleration in that direction? The answer is no. So for part B, we can write T minus mg cosine theta equals 0. Okay. Now, they want the ratio of T in position B through T in position A. Oh, and we got to finish this. So T is equal to mg cosine theta. So T in position B over T in position A is equal to mg cosine. I wrote theta here. I don't know why I wrote that. Of course I meant to write beta. All right, I'm sorry. Did I confuse you with that? I'm very sorry.
No, I understood the concept.
Yeah. So beta, and well, this is wrong anyway. And this is beta. Okay, so we've got TB is mg cosine beta divided by mg over cosine beta. Okay, so the answer is cosine squared of the angle beta. This is really a subtle point. It is so tempting to write this equation right here, in which case the ratio would just be 1. But it's wrong, because the acceleration in this direction is g sine beta, and the acceleration in this direction is 0. So if you're going to write down an equation like this, we have to do it along this direction, because it's in this direction that the acceleration is 0.
Okay, that makes sense.
Okay, good. All right, good problem.
Thank you.
More problems. Other issues, questions?
I have a question, Professor.
Go ahead.
On PIP chapter 5, question G1.
Okay, 5G1. Oh, this is the one with the springs. Okay, good. So the figure shows 2 different ways of arranging springs. So here's one way. Here's a spring. Here's a spring. And then we pull like this. The other way is like this. So here we say the springs are in parallel, and here we say they're in series. Boy, that's bad. Okay, this is another spring here. So there's 2 springs connected like this. And what are they asking for? The equivalent spring constant of the whole setup. So we want to replace this with an equivalent spring that looks like that. Now, each of these has identical spring constant K. And if we pull on this with a force F, okay, we haven't discussed the spring force yet, have we? I had forgotten that. Well, let's do that quickly. Here's a spring, and let's just put a mass here. The spring is in equilibrium. It's neither compressed nor stretched, and X equals 0. Now, if I pull the spring such that X is equal to X1, then the force that the spring exerts is equal to K times X, where K is called the spring constant. And the units of K are newtons per meter, obviously from the equation. So this is a model for a spring, what we would say would be an ideal spring. So the weight of the spring doesn't enter into it. We ignore the weight that the spring actually has, and we model the force it takes to extend it or compress it, a distance x1 is what I said, as K times x1. Now I'm assuming that compression and extension are going to be the same magnitude of force. But that only works for a spring that's loosely wound like this, right? Because I can compress it or I can extend it. But I can't very well compress a spring which is tightly wound like this, can I? I simply can't compress it. For this spring, I would say that the extensive force is Kx, but the compression force is not. But we're dealing with an ideal spring that I can neither extend or compress, and F is equal to Kx. Okay. So what do I write for this? Well, I write that the force, look at this situation here, this is K equivalent. A spring which is equivalent to these two, such that this force F gives me the same extension. So I have F equals K equivalent times the amount that I extended, delta X, that's for this. Now, what about for this situation? Well, here I have the force must equal K delta X plus K delta X, because these two stretch the same amount. Well, looking at this, we have K equivalent is just 2K. If these two springs were different, it would be K1 plus K2. Now, what about the series arrangement? Well, I want to replace it with this equivalent. So what do I have here? I have the amount that the two springs extend is the same. Here what I have is that the force on each spring is the same. So if I were to measure the force here, it would be the same as the force here. So let's write delta X that I extend this equivalent spring is the same as the delta X that I extend K1 and K2 individually. Add them up together, I get the total delta X. Well, from the force law, F equals Kx. Well, X is equal to F over K. So here, for this delta X, I have F divided by K equivalent equals, well, here I have F over K1 plus F over K2. So now my equivalent spring constant is equal to 1 over K1 plus 1 over K2. Now, if K1 and K2 are the same, then K equivalent is simply K over 2. So which of these two situations do you think is the stiffer spring? Louis, what do you think? Which is the stiffer of the two?
I think it's the series.
Well, in the series situation, my equivalent K is 1/2 K. So that means F equals K over 2 delta X. For the parallel situation, F equals 2K delta X. For the same delta X, which which of these two is the greater force?
Oh, the parallel.
Right, so the parallel is stiffer. Okay, that was a good problem. Okay, any questions on this? We'll go over the spring force in more detail during lecture.
What had to be equal for it to go from the F over K1 to being K over 2?
K1 and K2, if K1 and K2 are equal, here from this expression, if K1 and K2 are equal, then it's just K over 2.
Oh, okay.
Okay, other questions?
I was wondering if we could go over 5.104.
Okay. Oh, okay. Well, this is kind of interesting. So we have a block here, which is held by two equal length strings, such that this is 1.25 meters. This is 1.25 meters. This distance here is 2 meters, in which case we can define, let's say this angle here is theta. So what, the cosine? Oh, this distance here we're going to call r. So cosine of theta is equal to 1 over 1.25. So that tells me what theta is. And I know what r is because I know okay, now what's the setup here? This block is 4 kilograms. The system rotates about the axis of the rod. Strings are extended as shown. The tension in the upper string is 80 newtons. Okay.
Professor,
Yes.
I have one question.
Yes.
To calculate R, isn't it supposed to be 1.25 square minus 1?
Nah, I wasn't looking at it. I wasn't looking at it right. You're absolutely correct. You can do it more than one way. So R is equal to the square root of what? So 1.25 squared minus 1 squared. Okay, thank you for pointing that out. I don't know what I was thinking of.
Okay.
Okay, so let's do a free body diagram for M. We have mg. We have tension T2 at this angle theta. And we have tension T1, which is at the same angle theta. So they want to know what is the tension T2. So let's write our equations. Our equations are T1 cosine theta minus T2 cosine theta minus mg equals 0. Excuse me. And we know that T1 is equal to 18 newtons, 80 newtons. So T1 is equal to 80 newtons, so it's trivial to write down to solve for 2. Now, they would like to know how fast is this thing spinning? Well, we can do that by doing the forces in the horizontal direction. So T1 sine theta plus T2 sine theta has to equal what? Has to equal m times the centripetal acceleration. So there's an acceleration acting towards the center here. That is the A in F equals ma. Now, this is equal to m times v squared over r. So we have T1, we have T2, we can solve for v. Now it wants to know how many revolutions per minute does the system make? Okay, well, what is the period of the motion, capital T? How long does it take to go around once? Well, let's see. We have this is going to be equal to the circumference 2 pi r divided by v. Okay, now we know the period. How many seconds does it take to go around? So revolutions per second so I have 1 over t, which is equal to v over 2 pi r is in revolutions per second, right? So it takes 2 pi r over v seconds to go all the way around. 1 over t is the number of revolutions each second. Now we want to turn this into revolutions per minute. There are 60 seconds per minute. Okay, there you go. That will be the number of revolutions per minute. So 60 times v times 2 pi divided by 2 pi r. Now, what else do they want to know? I want the number of revolutions per minute at which the lower chord just goes slack. So for that part, what I want is for T2 to equal 0. Well, if T2 equals 0, then we have what? We have T1 cosine theta, so theta is going to be the same, equals mg. That's from this equation with T2 equals 0. So T2 just goes slack, the tension goes to 0. But the geometry is all identical. Now, what about this second equation? For the second equation, I have T1 sine theta equals mv squared over r. All right, so all I have to do now is substitute in for T1 and solve for V, and then use this formula right here. That's the speed at which, oh, we want the number of revolutions. Okay, so this is the speed at which T2 just goes slack, and then I plug into here to get the revolutions per minute. Now, what happens if the revolutions per minute is less than given by this? Well, if that's the case, then the angle theta will change, and T2 won't contribute anything to the dynamics because there won't be any tension in the second string. Okay, is that good?
Yes, thank you.
All right. Okay, other questions? All right. Let's see where we are in lecture. I think we've actually almost completed chapter 5. We've talked about the dynamics of circular motion, banking turn of an aircraft. We talked about the carnival ride, where you get plastered up against the wall as it rotates. Okay, there's only one more example I wanted to give you. This is a very famous problem that is actually quite subtle. I'm going to consider a wedge like this. Now, this wedge has a wedge angle theta, and I'm going to put a block of mass m on it. Now, this situation is a little bit different from what we've seen before. What we have now is that there's no friction on the base of this block, and there's no friction between the block and the wedge. I should have said between the floor and the wedge, there's no friction, and none between the block and the wedge. So as the mass m accelerates this way, the block is going to accelerate in that direction. So here's a problem with a mass on a wedge, and the wedge is allowed to move. It's not forced to move, like in the problem we looked at previously where we're pushing it. It's allowed to move under the reaction force of the normal force between little m and big M. We'll make this big M. Okay. So this is a little bit more complicated, isn't it? But let's do a free body diagram. Let's do a free body diagram for the mass little m. So we have mg. Notice I'm not going to play the trick of changing my coordinate system because that's not going to work because the wedge is moving. So I've got to still do the problem assuming X and Y are in these directions. We've got mg, okay. We have the normal force N of the wedge on the block, and that is the wedge angle theta. So that's easy. Now let's do the free body diagram for the wedge. For the wedge, I have big M times G. I have the normal force of the floor acting on it. And the only other force that acts on the wedge is the reaction force to this normal force. And that's it. All right, so let's write down our equations. Well, for this here, we have n cosine theta minus mg equals little m times what? The acceleration of the block in the x direction. So this acceleration that goes down here has a component in the x direction and has a component in the y direction. Now we can write another equation, which would be n sine theta, which is in, oh, I made a mistake. I'm so sorry. What was I thinking? This is the y direction, isn't it? When you see that I made a mistake like that, you've got to say something. Okay, that's obviously in the y direction. Now we have n sine theta must be equal to m times a in the x direction. Okay, that was easy. And how many unknowns do we have? We have two equations, and we have 1, 2, 3 unknowns. So we need more equations. Obviously, it's going to be the equation for the wedge. So let's write down the equations for the wedge. Well, I have the normal force minus big mg. Well, that must equal 0 because the wedge is not accelerating up and down. Now, in the other direction, I have, I left something out. Fn minus mg minus n cosine theta. Okay. Now, it turns out this equation is useless. We don't need it. Because it introduces the new variable Fn. But we're going to have, for our next equation, we're going to have what we need, almost. And that is going to be minus n sine theta is equal to big M times big A. So I could write A sub x, but A is in the x direction only, so I'm going to write it like this. Okay, so how many total unknowns do I have? I have 1, 2, 3. Here I have 4. If I include this equation, I have 5, but this equation isn't really needed because all it does is relate the normal force of the floor to the mass here and to the the normal force between block little m and big M. So I don't actually need this equation, but I do need another equation. So who wants to guess? Adam, I need another equation. What is it going to be? It's going to be the equation of
Um,
okay, let me give you a clue. As this M slides down, it's always attached to the wedge. So there's a constraint in the problem.
it doesn't move off of the wedge.
It doesn't move off the wedge. It stays attached to the wedge.
So it can't move up or down.
It can move up or down, but it stays attached to this surface here. It can't move off the wedge. It stays attached to the wedge. That's a constraint. So what's the equation called that's going to signify that fact? The equation of
Constraint.
constraint. That's right. I have an equation of constraint. The equation of constraint for this problem is rather difficult because I'm attached to this surface here, but this surface itself is moving. So let's continue this picture. Let's draw this picture. I'm going to erase the equation for Fn because we don't need it. But let's continue this picture here. Now, I have this angle theta. I have the acceleration of this mass in the x direction goes this way. And in the y direction, it goes this way. But what is this acceleration in the x direction? Is a sub x minus capital A, isn't it? Because the wedge is accelerating to the left with capital A. So the actual acceleration of this block is ax minus a, as seen by someone standing here watching everything move. And my a sub y is over here. So I'm going to treat a sub y as an inherently positive number. That means that ay over a sub x minus a is equal to the tangent of this angle, but this angle is minus theta. So the tangent of minus theta is minus the tangent of theta. So that's my equation of constraint. So now what are my unknowns? 1, 2, 3, 4. And I have 1, 2, 3, 4 equations. This is much more involved to solve, but you can do it. And I will give you the answers. The acceleration capital A is equal to minus mg tangent theta over little m plus big M tangent squared theta plus big M. And A sub x is equal to big M G tangent theta. Oh, divided by the same thing. Little m plus big M tan squared theta plus big M. And little ay is minus little m plus big M. G tan squared theta over little m plus big M tan squared theta plus big M. Okay. So if you go through all the algebra, and it's very tedious, but it's straightforward, to solve for all of these variables, that's your answer. Now, here's what I want you to really understand. I want you to understand where these first three equations came from. These equations come from the free body diagrams for big M and little m. This is more subtle. I won't expect you, in general, to be able to write down an equation of constraint this complicated. But you might think about what it means. So we have ax minus a this way, ay here, we've got minus theta. If you draw yourself that little picture, you can sort of figure it out. Okay.
I just had a question to clarify something.
Sure.
I was looking down at my notes while you were drawing the picture, but for the wedge, the arrow for big A's to the left, was that to indicate that the wedge is moving to the left?
Yes,
Okay.
it will. And just from common sense, you expect if little m slides down,
Mhm.
there's a force on the wedge that's the normal force of little m this way. Well, that has a component in that direction, and it's that which accelerates the big wedge. In fact, that's
Okay.
what this equation says. The component of this normal force is what accelerates the
Okay.
big wedge.
All right. Thank you.
Okay, good. All right. Well, that actually completes chapter 5. Oh, chapter 6 for the spring force. Okay, so let's just do it. Let's begin chapter 6. Are there any questions? Any questions on anything so far? Pip and MD are always open for discussion. Any questions at all? Okay. Okay, chapter 6 is called Work and Energy. And very first thing we're going to discuss is something called the work energy theorem. It's very fundamental. In fact, from this, we're going to get our understanding of what energy is. So let's consider Newton's second law, F equals ma. Well, I can write that in a different way. I can write that as m dv dt. Everybody's okay with that, right? I could also write d squared x dt squared, but that's not what I want to write now. Because I want velocity to be part of this. I'm going to write this in still another way. M dv dx times dx dt. Now, by Leibniz's rule, I can treat differentials as if they are Algebraic quantities. So dv dt is the same as this right here. So let's finish this by writing this as m dv dx. And what is the dx Andreas, what's the dx dt?
Just velocity.
Is just v, the velocity. So now I have a differential equation that says f is equal to m v dx. I'm going to separate this as f dx equals m v dv. And now I'm going to integrate both sides of this from position 1 to position 2. And at position 1, my velocity is v1. And at position 2, my velocity is v2. So this becomes f x2 minus x1 equals 1/2 m v2 squared. Now I did that integration in my head. Is everybody okay with that? V dv is 1/2 v squared, right? Minus 1/2 m v1 squared. Now, this term goes by the name of work. And these terms go by the name of kinetic energy. So what does the work energy theorem say? The work energy theorem says the net work in going from position 1 to position 2 equals the change in kinetic energy from position 1 to position 2. Now, in general, this is a one-dimensional argument here. But actually, in general, work has a much more general definition. The work W is equal to the integral from position 1 to position 2, and it doesn't have to be on a straight line. Here's position 1, here's position 2 of f dot dr. And what does this integral mean? Well, this is a new kind of integral. This is called a line integral. In the past, you're familiar with a function f of x that looks like this, and you integrate f of x over the x-axis, don't you? Between position 1 and position 2. Well, now what you're doing is you're saying that instead of integrating over the x-axis, you're integrating over a path. So the path is no longer restricted to the x-axis. The path, in principle, is any path at all. So let's say we have that as my path. Well, now how do I evaluate this integral? Well, at every place along this path, there is a force vector. Let's say at this point, the force points that way. dr is in the direction of the path, which in this case, I'm not drawing this well, it's tangent to this path. So this is dr. And f dot dr is nothing but f cosine of theta dr, where this is the angle theta. And you repeat this for every point along this line and add up all of these terms f cosine theta over the path. Okay, not always as easy to evaluate as an ordinary integral. This is called a path integral. Integrals that have this form are called work integrals. And you will see work integrals in electromagnetism all the time. Okay. All right, so that's the definition of work. Work is the force dotted through a distance. And in this example here, it was very simple. It was a one-dimensional problem. The force was acting along the x-axis, and I went from x1 to x2. Now, what about this thing? A term of this form is called kinetic energy. Now, kinetic energy in work must obviously have the exact same units. And those units are joules. So work or energy has the units of joules. And a joule is sometimes written as a Newton meter. You could also write it, looking at this term, if you wanted to, as a kilogram meter squared per second squared. That's the same thing as a Newton meter. And we call that a joule. I'll spell it for you. Joule, for James Joule. Okay. Now, let's look at this equation for the work energy theorem. And let's adopt the convention that positive work is work done on the body. That's the way I've written this. That's the way I've written this integral. And that's the way I've written this integral. So if that work turns out to be positive, then work is being done on the body by the force. Okay. Now, if work is done on the body by the force, it's a positive work, and that means that the change in kinetic energy, so this term is equal to the change in kinetic energy the change in kinetic energy is positive. If I do work on a body, I make it speed up. If the work is negative, the body is slowing down. So let's consider the case of, here's the ground, and here's a block of mass M. It's initially at rest, and I drop it. Is it speeding up or slowing down, Lewis? As it falls, is it speeding up or slowing down?
It's speeding up.
Okay, so if it's speeding up, then is work being done on it, or is it doing work?
Work is being done on it.
Work is being done on it. Okay, so if I drop it, the gravitational field or the gravitational force mg is doing work on this body, and when it goes from y1 to y2, it must be speeding up. And work that's done by gravity in this case is going to be, let's say this distance is d, is going to be mgd. Now there's a couple of good mnemonics in here. FDR, what does that make you think of?
The president?
Franklin Delano Roosevelt. Okay.
Yeah.
So work is FDR. There you go. That's great. What's the work done by a block that's dropped a distance d in the Earth's gravitational field? MGD. I'm sure that stands for something. Does it? Maybe you guys don't drink. I think it stands for Miller Genuine Draft. I think it's a beer. Okay. Now, let's do some problems using these facts. Here
So
is,
I had one question, just briefly. So for angle theta, is that between F and DR or F and the path?
well, the dr is tangent to the path.
Okay.
So it's between theta. Theta is between F and the tangent to the path.
Okay.
So they're both the same thing. Okay, so here's the ground, and I am going to throw a ball, mass m, straight up with velocity v0. I'd like to know how high it gets. Well, that's easy. I can use the work energy theorem. It ascends to a height h. What is the total work done on the ball? Now, the work energy theorem means the total work is the change in kinetic energy. The only force acting on the ball is the force of gravity. So what is the total force, total work done by gravity? Well, the force of gravity is m times g, and it acts over a distance h. So you're tempted to say it's mgh, but the force is in this direction and the motion is in this direction. So F dot dr is negative. That's a general rule. If the force and the displacement are in opposite directions, the work will be negative. If they're in the same direction, the work will be positive. So that means that the work done by gravity here is going to be minus mgh. That has to be equal to the change in kinetic energy? Well, it starts off initially with kinetic energy 1/2 mv0 squared. But when it gets to the top, it's not moving because it's a turning point. That means that its velocity is 0. So our change in kinetic energy is minus 1/2 mv0 squared. And what is the height that it attains? Is going to be equal to v naught squared over 2g. Now think about how easy that was. Did you need to use multiple kinematic equations and solve simultaneous equations or any of that stuff? You didn't have to do any of that stuff. This is the beauty of energy methods. So we're going to learn 2 basic energy methods. The work energy theorem is always true. Conservation of mechanical energy is true for conservative forces. So, and we'll explain what that means. So those are the 2 tools we have for energy methods, is the work energy theorem and conservation of total mechanical energy. And they're very easy to use because all you need to know is something about what's going on at the end points of the motion, or at least the points of interest in the motion. You don't need to know what's going on in between. All right, let's do another problem. Let's do the opposite problem. I'm going to drop a ball, but I'm dropping it from rest. How fast is it going just before it hits the ground? Well, the total work done by gravity is mgh. Why is it positive? Because the force acts downward and the motion is downward. That equals the change in kinetic energy. Well, it hits the bottom and it's going at speed, let's just call it v, and its initial kinetic energy was 0 because it wasn't moving. So how fast is it going when it hits the ground? It's 2gh square root. Again, completely trivial. Let's ask a third kind of question. How fast is it going when it reaches a height h on 2? Well, let's start from throwing it upward. So I'm throwing it upward with speed v0. How fast is it going when it reaches height h over 2? So half of its maximum. Well, what's the total work? The total work in that case is minus mgh on 2. And that must equal the change in kinetic energy, which is 1/2 m, let's call it v1/2 squared, minus 1/2 m v0 squared. So just solve for that. And you can play this game for any place between the ground and the maximum height. And you can play the game throwing it from a height or throwing it from the ground. It doesn't matter. Okay. Let's look at the problem that I promised to show you last time when we talked about friction. So we have a surface, and I have a box, and there is a coefficient of kinetic friction mu, and right here at x equals 0, it's moving with a speed V0. So I would like to know, how far has it moved when the object comes to rest? So when the object comes to rest, what is this right there? Well, I can use the work energy theorem. The frictional force acts this way, and the box is moving this way. Therefore, the work done is negative. I also know the work is negative because the box is slowing down. So the work done on the box is negative, and it's equal to minus, what is the frictional force here? The frictional force is going to be mg mu times this distance that it travels, x. That's the total work done. What is the change in kinetic energy? Kinetic energy final is 0. Initial is 1/2 v0 squared. The change in kinetic energy is minus 1/2 m v0 squared. So now solve for x. Wasn't that simple? Most of these problems are very, very simple. I tell you what, I'm gonna pose for you a problem. I'm gonna let you think about it. And I'm gonna let you think about it during break. So here is a cliff. And let's say this cliff is 100 meters. Down here at the bottom, I have y equals 0. And there is an injured person in a stretcher. Who's being hauled up the side of the cliff by these rescuers who are hauling on the rope. Now, from y equals 0 to y equals 10 meters, so I'll write meters, I go from v equals 0 to v equals 1 meter per second. Then I stay at a constant 1 meter per second until y equals 90 meters. And at y equals 90 meters, my speed is 1 meter per second. And here at the top, just before the rescuers grab him and swing him over the cliff, v is equal to 0. So I'm accelerating this guy for 10 meters to 1 meter per second. He's moving with a constant speed of 1 meter per second. Then I'm slowing down from 1 meter per second to 0 over the last 10 meters. So let's call this regime number 1. We'll call this regime number 2. We'll call this regime number 3. And what I would like to know is, in each of these regimes, what is the work done by gravity, the work done by the rescuers, and the total work that's done? Okay. Now, let's take a break. And I'll see you at, well, let's have a nice long break. Let's go till 3:15. and you can go get refreshments and come back and look at this problem and start filling this out. And then we'll go around the room and have volunteers fill in the table for us, okay? Oh, I got to tell you what the weight of this guy is. Okay, so the mass of the man in the stretcher is 80 kilograms. You need that to know that. But now you've got everything. Okay. See you at 3:15.